And here we are, this is the last topic for the GCSE specification. This is C12, the Earth's resources. So first of all, we look at finite and renewable resources. Why do we need resources? Well, for warmth, shelter, food, transport. A finite resource is one that is used up at a faster rate than it is created. For example, limestone to make cement, crude oil to make diesel and polymers, metal ores. A renewable resource is created at the same rate or faster than it is being used up. For example, plants, wood chips can be used to make fuel, ethanol can be used to make ethene and therefore plastics. And then we've got this term sustainable development, which is meeting the needs of the current generation without compromising the needs of future generations. So in order for that to happen, we need to decrease our use of resources, and we might need to look at using renewable resources. And we have our 3 R's: reduce, reuse, recycle. We need to be reducing our use of high quality resources. For example, we need to be using sustainable chemical processes, and to do that we need to be picking sustainable alternatives, picking the low energy option. That's going to be cheaper, but it's also going to be better for the environment, conserving fossil fuels as well as decreasing combustion, decreasing the amount of CO2 into our atmosphere, and therefore lessening the effect of the enhanced greenhouse effect. We also need to be using renewable resources. For example, there are 2 ways that we can make ethanol. We can heat ethene to 300 degrees C, or we can ferment glucose. Glucose is a renewable resource. It's sugarcane. It comes from plant sources. And I'm just going to put in here the topic of orders of magnitude, which is essentially rough estimations. We might be asked, for example, we are going to dissolve 0.21 grams of sodium in 0.0125 decimeters cubed of water. Calculate the concentration to the nearest magnitude. So what we do is we estimate our sodium, 0.21, to the nearest order of magnitude. So that's going to bring us to 0.1 grams. And we need to estimate our 0.0125 decimeters cubed to the nearest order of magnitude, so we can round that one down to 0.01 grams. And then we know that concentration is simply amount over volume, so 0.1 divided by 0.01 gives us 10 grams per decimeters cubed. Treating wastewater, the first thing that we do is screen the wastewater. We pass it through a big metal grid to trap large objects like branches. We then pass that wastewater into the primary tank. This is when grains of sand and stuff is left to settle via sedimentation to the bottom of the tank. We have paddles that move the sediment round and the piping the sludge into the middle of the tank essentially, and that can then be piped onto the sludge treatment plant. The effluent, that means the liquid component of the tank, is then piped onto the next tank, which is the secondary tank. In the secondary tank, useful bacteria are employed to digest organic matter and microbes. They do this via aerobic respiration, and that means that the tank needs to be aerated. The rate of this aerobic respiration depends on the size of the tank as well as its temperature. And then we have the final tank. This is when useful bacteria are left to settle down to the bottom via sedimentation. They are then reused in the secondary tank or piped onto the sludge treatment tank. At the final tank, this wastewater is now declared safe and it can be discharged into rivers. However, if we are in a especially sensitive ecosystem, that wastewater will be then passed through a sand bed and sterilised. However, we will not use chlorine, and that's because chlorine can build up to form toxic organic compounds. In the sludge treatment plant, organic matter is digested by microorganisms anaerobically. The sludge is then dried out to form a crusty cake and burnt to produce electricity. Alternatively, sludge can be used as fertiliser, or the biogas produced can be burnt to produce electricity. However, that biogas could also be cleaned to produce methane, which is natural gas. If we increase the temperature of the tank, anaerobic digestion will happen at a faster rate. However, it will become more expensive. In treating sewage and agricultural wastewater, we need to be removing organic matter as well as harmful microbes. In treating industrial wastewater, you need to be removing organic matter as well as harmful chemicals. Potable water. Potable water is water that is safe to drink. Freshwater sources include aquifers, which are essentially wells in porous rocks, so rocks with little holes in. How do we obtain potable water from freshwater? Well, step number 1, we screen the water. We pass it through a large metal grid to trap large objects like branches. We then allow sedimentation to occur. Step 3, we add aluminium sulfate and lime to act as a binding agent, binding dirt together, which can then be transported to landfill sites. We then pass that water through a filter bed and sterilise it. To sterilise it, we can add ozone, chlorine, or we can pass through UV light. We then pH test the water and correct it using a meter. And step 7 is just storing that water in a reservoir. But for coastal countries, how do we obtain potable water from salty water? Well, this is a process called desalination that can be done in 2 ways. The first way is distillation, but distillation involves high amounts of energy, and that makes it really expensive. The other way we can do it is reverse osmosis. We pass the water through membranes to separate out the salt from the water. However, this involves lots of energy, high pressure, and the salt causes corrosion of the pumps. The solution to this is to use flash distillation, which involves low pressure and lower energy. The next topic is life cycle assessments, or LCAs. These essentially list inputs and outputs of energy. They evaluate the environmental impacts of something. Importantly, there are 4 stages in a product's life: extracting and processing raw materials, manufacturing and packaging, the use and reuse, and disposal at the end of useful life. We also have transport and distribution between each of the stages, which often releases CO2. Commonly, you might be asked to do an LCA on a plastic versus a paper product, so we're going to do a plastic bag versus a paper bag. Well, stage number 1 for a plastic bag, we use crude oil, which is a finite resource. It requires lots of processing, however it's incredibly efficient and produces little waste. For a paper bag, we use large amounts of timber. Timber is a renewable resource, but we then need to pulp it and process it. This requires lots of energy and lots of water, as well as producing lots of unusable waste. Stage 2 for both the plastic and the paper bag is the same. It's essentially rolled into large sheets and cut to shape. This requires lots of machinery and lots of energy, but they are stored in cardboard boxes. Stage 3 for a plastic bag, well, they are reused because they're quite strong, but for a paper bag they are weak and therefore they can only be used once. Stage 4, plastic bags are recyclable with large amounts of energy, but they are not biodegradable and often go to landfill. That takes up space as well as polluting the ground. For a paper bag, again, they are recyclable with large amounts of energy, but they are biodegradable. They are not toxic and they are not polluting. For the transport and distribution between each stage, for a plastic bag, we can actually fit 10,000 bags per meters cubed, so we can transport many plastic bags with less carbon emissions needing to be released. And for a paper bag, we can only fit 7,500 bags per meters cubed, so you decide which is better, which is more sustainable. However, there are issues with LCAs. It's very easy to quantify the use of water, energy, resources and waste produced, but it's not easy to quantify the effects of pollutants. And because of this, we use value judgments, which are subjective. As well, LCAs can often be misused due to bias. The scale of the impact is also a problem. Equal weighting is given to local, regional and global problems caused, and no consideration is taken to cost or performance. Solutions to these are to peer review LCAs, especially to avoid bias, but also if we're using numerical data, to only use widely accepted data. The next topic is alternatives to metal extraction. Copper is often used in electrical wiring, but copper-rich ores are finite. Typically, copper is extracted via smelting, or it's reacted with sulfuric acid to produce copper sulfate and is then extracted via electrolysis. But these traditional methods are increasingly becoming uneconomical and very harmful to the environment. One solution is phytomining. This is when plants are grown in soils containing low percentages of copper ores. Plants absorb the metal compounds from the soil. They are then harvested and burned to produce ash, which is then dissolved to create the metal. Advantages include we use soil with low-grade ores, no mining takes place, it can help to decontaminate the ground, and we have low CO2 emissions. Disadvantages, however, include specific growing conditions are required, and plants may require added minerals to the soil, which can be expensive. Also, not very much is extracted, and the process is incredibly slow. An alternative solution is bioleaching. This is when low-grade copper ores are added to bacteria to produce a leachate solution. Copper is then extracted via electrolysis with Cu2 plus ions moving to the cathode, or using displacement with scrap iron. Advantages include, again, we use low-grade copper ores, no mining is required, low energy costs, low sulfur dioxide emissions. Disadvantages include toxic chemicals are produced and the process is very slow. Just a quick recap then of carbon footprint versus LCA. Well, carbon footprint measures the total amount of CO2 as well as other greenhouse gases emitted over the full life cycle of a product, service or event. And LCA measures the total environmental impact, including water use, non-gaseous pollutants and waste produced, as well as greenhouse gases. And our final topic is reducing use. We need to reduce our use of metals, glass, ceramics. These are finite, raw materials. We need to conserve our natural environment, and quarrying and mining completely devastates that. We need to conserve finite materials, which include fossil fuels. Huge amounts of energy is needed to process these raw materials, as well as huge amounts of water. We can also reuse materials. For example, glass bottles can be crushed down and melted back down to create more glass bottles. And we can recycle materials to create a different product. For example, metals can be melted, then recasted or reformed to create a new product. The amount of separation required depends on the material and the final properties of the product. Scrap steel can be reacted with iron from a blast furnace to decrease the amount of iron needed extracting. And that's all for this final chapter, so huge congratulations and humongous good luck for the exams.